Hello. The topic of the new chapter we're starting is chemical equations and reactions. Let's begin by asking a question we considered earlier in the year, which is, what is a chemical reaction? Well, we talked about this in chapter 1. A chemical reaction is a chemical change in which one or more chemical substances are converted into different substances, and we now understand that this happens by making and breaking chemical bonds. What evidence might you have that a chemical reaction is taking place? Well, you've seen enough chemical reactions in this classroom to know what indicates a chemical reaction is occurring. And there are several different possibilities. You might see a change in color. You might see formation of a solid or release of a gas. You might observe a change in temperature, either an increase or decrease. And in some cases, you can see light being given off. The last question is, what is a chemical equation? Well, a reaction is what actually takes place in the laboratory. A chemical equation, on the other hand, is a symbolic representation of the reaction using chemical formulas to represent the substances that are reacting. Every chemical equation has the same generic form. We show on the left-hand side the formulas of all of the reactants, that is, those substances that you're starting with, an arrow pointing from left to right to indicate reacts or forms or yields, and then on the right-hand side of the arrow, the formulas of all of the products. So the question is, what must be the case for a chemical equation to be written correctly? Well, there are three characteristics that one always observes. The first characteristic is you have to include the formulas of all of the reactants and products. Any substance, whether it's an element or a compound that takes part in the reaction on either side has to be included in the equation. Second characteristic is that all of the formulas have to be correct and they have to show the correct physical states of the reactants or products. Now I'm about to show you a bunch of factual information that you do not need to memorize. For this unit, you will, on the test and quiz, have 1 page of notes in which you can write anything you want, and what I'm about to show you is some of this factual information. First of all, elements occur in certain molecular formulas. Hydrogen, nitrogen, oxygen, and all 4 halogens are diatomic molecules. That means the formula must have the symbol of the element with a subscript of 2. It turns out that there are 2 nonmetals, phosphorus and sulfur, that just happen to occur as polyatomic molecules. The most common form of phosphorus is a molecule in which there are 4 phosphorus atoms, P4, and likewise the most common form of sulfur is octasulfur, in which there are 8 sulfur atoms. Everything else on the periodic table is monatomic, so you would not include any subscripts, simply the element symbol. You need to have the correct physical states of the elements. Hydrogen, nitrogen, oxygen, fluorine, and chlorine, and all the group 18 elements are gases. There are only 2 elements on the periodic table that are liquids under normal conditions, and those are mercury and bromine, and everything else is a solid. One random bit of factual information you need to write on your note sheet is that pure ionic compounds are always solid. And then finally, you have to indicate the physical state by writing a symbol after the formula of the element or compound to show the physical state. So if it's a solid, you would put a lowercase s in parentheses, liquid L, gas G, and there's a 4th pseudo-state that you may not have thought about before, and that is aqueous, which means dissolved in water. So if a substance is dissolved in water, the correct physical state is not liquid, it is in fact aqueous, represented by AQ. So those are the first 2 characteristics of a correctly written chemical equation. The third characteristic is that it has to satisfy the law of conservation of mass. Well, what does that mean? Well, it means that however many atoms of one element you have on the reactant side of the arrow, you must have exactly that many number of atoms on the product side. Otherwise, you would be implying that you were creating or destroying atoms, which we know doesn't occur. Or another way to say this is that the equation has to be balanced. And I'm pretty sure that all of you at one point or another in a previous science course have talked about balancing equations. We're going to go over that in more detail this year. So here's what I expect you to be able to do. If I give you a verbal description of a chemical reaction, meaning a sentence that describes exactly what the reactants and products are in the chemical equation, you should be able to write an equation that includes everything, that has correct formulas and physical states, and is balanced. So let's take an example of that. Hydrogen and oxygen react to form liquid water. I want to write a balanced equation having correct formulas and correct physical states to represent this chemical reaction. So here are the steps that we're going to go through. Step number 1, we're going to write the correct formulas on each side of the arrow. make sure you put the reactants on the left side and the products on the right side. Step number 2, we're going to add physical states. And then finally, we're going to balance it using a method that's called by inspection, which means essentially trial and error. Normally, you'll begin by listing what's called the atom inventory. That is a list of how many atoms of each element are on each side of the arrow. It's a good idea to pick out the most complicated formula on either side of the arrow and begin by balancing the elements in those. In order to balance the equation, you have to add or change coefficients. Coefficients are the numbers that come to the left of the formulas that tell how many atoms or molecules of that particular substance you have. And every time you add or change a coefficient, you update your inventory by indicating the change in the number of atoms of each element. If there is a polyatomic ion involved in the reaction and it does not undergo change, it's best to balance not by element, but in fact by polyatomic ion. I'll show you an example of this in a minute. And then finally, save any pure elements for last. If one of the reactants or products is an uncombined element, that will be the last one that you want to balance because you can balance it by simply putting whatever coefficient you need. Finally, go back and check. Make sure that you count very carefully to see that you have the same number of atoms of each element on each side of the arrow. So let's go through this example. Hydrogen and oxygen react to form liquid water. Step number 1, write the correct formulas of the reactants and products. Hydrogen we know is diatomic. Oxygen is also diatomic. They react to form water, H2O. I'll add my physical states. Hydrogen and oxygen are gases. Water is a liquid. So I've got all reactants and products, I've got correct formulas, and I've got correct physical states. The last step is to balance it. So I will do my atom inventory. I'll list the elements and count the number on each side of the equation. I've got 2 hydrogen atoms on the reactant side, 2 oxygen atoms on the product side. I've got 2 hydrogen atoms on the product side and 1 oxygen atom on the product side. So my hydrogen is balanced, but oxygen is not. So in order to get my oxygen to balance, I need another oxygen atom on the product side. So I will add a coefficient of 2, thereby giving me 2 oxygen atoms to balance oxygen. The problem is that also gives me 4 hydrogen atoms, and now hydrogen is not balanced. Well, that's easy enough to fix. I simply add a coefficient of 2 before the H2, giving me now 4 hydrogen atoms as well. Notice that we balance elements by changing coefficients, not by changing subscripts. You cannot change the formula of a reactant or product in order to get atoms in it to balance. You can only change coefficients. So here is the final answer, our correctly written and balanced equation. And we'll pause here for a moment.